In this lesson, we're going to look at lines of best fit. When we collect real data, it very rarely produces a perfect straight line, but a clear straight line trend is present. Modeling such data with a linear model is a good start at understanding the relationship between the variables involved. Here we can see some data that clearly has a straight line trend, and we can see a line has been approximately fitted to it. This line is called a line of best fit. The simplest method is to use a ruler and you draw your line on the graph that seems to balance out the points around the line. This is called fitting a line by eye. In maths, there's all sorts of ways of finding a line of best fit, as we'll see later, to minimize the variation between people. To create a linear model for the line, we can approximate the y-intercept and slope from the line we draw, or we could choose 2 points on that line to make that linear model. When we use this method, there can be variation between people, and if you look your answers up in a textbook, you might see some difference, and that's normal. To minimize this sort of variation that occurs when people choose different points, we follow some processes. If we have access to the actual original data and we notice that our line of best fit uses or passes through one of those original points of data, we would use that coordinate. Sometimes we might have 2 coordinates, which is what we need for the model. If that doesn't happen, maybe we only have 1 or none, we can then look at the way the grid lines are presented on our graph, and if we see that our straight line lies on one of the grid line intersections, we could use that point because it's easy to read the scale off. The last thing we do if we have to is we use the scale on the axis to estimate the coordinates on the line, and we may need to use a ruler to work out a proportion to find such estimated coordinates. Generally, if we do have to estimate the 2 points, choose them as far apart as possible, and that'll minimize the error for the slope calculation. Once we have established our linear model, we can use it to make predictions. If you use the linear model to make a prediction within the range of the collected or provided data, it is reliable to the same degree that the data is scattered about the line of best fit. This is called interpolation, and that's where we use the model to make a prediction within the range of data. It is less reliable than making predictions outside the range of data. When we do this, it's called extrapolation. Let's look at an example. Here we can see some data around the travel time in minutes between cities flying by plane, and the distance between cities is in kilometers. So our 2 variables are capital T for the time of travel and lowercase d for the distance between the cities in kilometers. Now, if we look at this data, we could probably see one obvious point straight away there, and that would be a good point to choose. And also, this point here does lie in the data, but I don't have access to the actual numbers from the raw data. We've just been given the graph, so I can either choose that looks like a grid line intersection, or I could estimate the y-intercept. I'm going to go for this point for my 2 points, and let's write them down. So this point is halfway between 500 and 1000, which is 750. That comes first. And our T point is 100 minutes. And our second point is 3,500 kilometers. And halfway between 300 and 350 is 325 minutes travel. Okay, let's look at the gradient between these 2 points. So there's our gradient triangle, and we've got 325 minutes minus 100 minutes gives us 225 minutes. And the horizontal distance for our positive gradient here, because it goes up to the right, is between 3,500 and 750, which equals 2,750. So we can calculate our slope is positive, the vertical distance at the top, and the horizontal distance at the bottom. And it does have some units of measurement. Vertical distance is minutes per horizontal distance is kilometers. So minutes in travel time between cities compared to the kilometers between cities. So rounding that off to just 1 sig fig would be what our gradient is. So our model for y equals a plus bx, y is t, equals a plus b, which we worked out to be that, and our x is d. So we have to find what this y-intercept is. We can see it's about, I reckon, about 40, and we need to substitute one of our points. I'm going to use the one with the smaller numbers, 750 minutes travel time compared to 100 kilometers between the cities. And this is my distance between the cities, and this is my time in travel. Replacing those coordinates, we get 100 equals a plus 0.08 times 750. And so 100 equals a plus 60. Change the side, change the sign. And we can see, as we estimated before, the y-intercept or the t-intercept is 40 minutes. I wonder what that physically means. It may not have any meaning in this problem. So our model is t equals 40 plus 0.08 d. Let's use this to make some predictions. So what if a city was, two cities were 2,500 kilometers apart? What would we expect the travel time to be? So we use our model t equals 40 plus 0.08 times 2,500. Do that on our calculator, and that would give us 240 minutes. So to travel between cities that are 2,500 kilometers apart would take about 240 minutes with 4 hours. So if we change that to a new distance between two other cities, say they were 4,500 kilometers apart, then we can replace d with 4,500, put it into our calculator, gives us 400 minutes travel time for that city. Finally, just a reminder of what the slope means. So the slope b was 0.08. The vertical distance, its travel time in minutes per kilometer between cities. In other words, 0.08 of a minute is the travel time per kilometer between the cities. So if we happen to change that to seconds, we times it by 60, we get 4.5 seconds per kilometer between the cities. Or another way of looking at it, if we change that to 100 kilometers, we times by 100, it would be 8 minutes per 100 kilometers between cities. So that's the meaning of the gradient. I hope that helps you with your questions.